Okay, well then, now we continue with the lecture. All right, so the last thing that we saw was the 3D Mohr circle. And the 3D Mohr circle help us understand and calculate shear and normal stresses for faults or for fractures at a given angle. And also, we learned that these lines, these circles, correspond to faults that contain at least one of the stresses, and everything in between is something that is not aligned with any of the stresses, but those are all possible state of stresses, and those are what we call oblique faults. All right, so what we're going to do right now is we're going to use the Mohr circle to calculate a given normal stress and shear stress for any of these planes. So the objective is that for a given state of stress and for a given strike and dip of a fault I'm going to give you, that you should be able to tell me which Mohr circle to pick and which angle to pick over here too, in order to tell me what is normal stress and shear stress. And later we'll see what we do with this inside the three circles. But on the circles themselves, you can do that. It's very simple math. You just have to recognize which circle to use, which angle to measure, and simply then utilize these equations. Sigma n and tau, center plus the radius of the circle times the cosine, and tau is just the radius times the sine. So it's very, very easy to remember. Okay, so we'll go with the first example. And we'll do it step by step. All right, so this is what you know. You know the state of stress. You know vertical stress. You know maximum horizontal stress. And you know minimum principal stress. It's not enough to get to know the value of stresses at a given place, but also you need to know the orientation. And we'll assume that this one is a principal stress. And as soon as we know that one vertical stress is a principal stress, the two horizontal stresses must be also principal stresses because they are perpendicular to the vertical stress. I'm going to also tell you that SH mean, it's at an angle of 90 degrees going from the north towards the east. So it's in direction east-west. I'm going to tell you one more thing over here, is that we know the pore pressure at this given place, and it's 10 megapascals. That's all we know about the state of stress. All right, here's the second part. Information about the fault. We know that this fault has a strike of 0 degrees and has a dip of 60 degrees to the east. And with all of this, my question is, what is the value of sigma n on the fault? What is the value of tau on the fault? And also something very important that we're going to get to see that is very meaningful is what is the value of shear stress divided effective normal stress. So that's what we have to answer. Remember that we want to know this because when this ratio approaches the friction coefficient, then we get close to slippage of the fault or reactivation. All right. So if you apply this general procedure, then all problems are going to be more or less the same. And they should be easy to solve. Okay. Question number 1 that you should do. Identify the stress regime, which in this case is what? Normal. Very well. All right. Second, we're going to make an schematic of the in situ stresses and or with the fault, okay? And there are two options for this. Here you can make a block diagram, which is the cube that we have been drawing so far, but some other times when some of the stress is not aligned with east-west or north-south, it's just easier to do a top view. Let's go now with a block diagram. All right, a block diagram of this case, we just need to put all these stresses into a block diagram and the fault too. And I chose the block diagram because look at the strike of the fault. It's in the direction of which stress? I'm going to start drawing, but you start thinking about that. My stresses, and I'm doing the block diagram too because my stresses are aligned with east and west. For example, here I know that my minimum principal stress has an azimuth of 90 degrees, which means that from the north, 90 degrees, I get to the east. So this is the direction of SH mean. Of course, vertical stress is going to be in this direction, and SH max is going to be going in direction north-south. Okay. And what about the fault? The fault has a strike, yes.
Oh, never mind. I was going to say the fault is northwest. South.
North-south, right? So the strike, remember, strike is intersection of the horizontal plane with the fault itself, is north-south. And before I draw it, I'm going to look at the dip. It's dipping towards the east. So in order to do that, it's going to be a fault that's going to be dipping towards the east. So I'm going to draw it somewhere over here. The fault is going in direction then north-south, and with a dip of 60 degrees. All right, so we have the fault, we have the stresses. Yes, Mr. Baraki.
Which line is the strike?
This line is the line of strike. It's the intersection of the plane of the fault with the horizontal plane. All right, so we have the block diagram, and then we have the fault in there. Now we need to identify the corresponding circle that we're going to use for the Mohr circle, the 3D Mohr circle. So remember, with 3D circle, but we don't have to use all of them in this case. We just need one. So I'm going to put here, identify Mohr circle. With that, I mean, I want to know which are the stresses that are going to play a role in defining what is sigma n and what is tau on this fault. Remember, sigma n is the normal stress, and tau is the shear stress. Okay. So from here, can you see that the fault is in the same plane as the direction of SH max? So what that means is that it doesn't matter what is the value of SH max, because it's not going to have any projection on the plane of the fault. The only ones that are going to project on the plane of the fault are SV and SH min. So when I project those stresses on the plane of the fault, those are going to change my normal stress and my shear stress. But SH max is not going to change that at all. And in more like geometrical terms, so we can say that this stress is aligned with this plane, and because of that, that's not going to intervene at all in the determination of shear and normal stress. So the Mohr circle that we have to draw is just a Mohr circle that has SV and SH min. Before we draw the Mohr circle, we need to calculate effective stresses. Let me write this, and then we'll do that. Okay. So you have the values there in your page. I have them too. I can see them from here in my page, but I'm just going to write what we need to calculate right now. Remember, Mohr circles should be always drawn with effective stresses, not with total stresses. Because when you draw it with total stresses, it gets a little bit confusing, because you cannot put a shear criterion in there. And you should always do it in terms of effective stresses. So let's do it in terms of effective stress. That means that first we need to calculate all the effective stresses. All right, what is sigma V? No, that's SV. No. 23 minus 10, okay, and that is 13 MPa. And sigma H min is going to be, in this case, 3.8 MPa. And sigma H max is going to be something, but I don't really need it, so I'm not going to write it. These are the two I need. And when I draw the Mohr circle, I'm going to have sigma V equal to 13. So let's say this is 10, 5, 15, 13. This is sigma V, and sigma H min is somewhere over here. And the circle, we have the 2 points. We can define the circle, right? For this circle, what's going to be the center? 13 plus 3.8 divided by 2. Can you make that number? Can you calculate that? How much? 8.4 MPa. Remember to put units. Units are very important. And the radius is? That should be 13 minus 3.8, which is You have a calculator, guys? I don't have one. So that should be 3 plus 6, 9, 4.6 MPa. And all right, so the center is going to be somewhere over here. This is going to be my circle. This is the center, and we have a radius. Okay. Now, we need to find the angle. So, because the Mohr circle represents all the possible state of stresses for a fault going from the plane of SV to the plane of SH mean. Now, the angle that you have to use here is going to be always the angle between the plane of the maximum stress that you're looking at currently and towards the other stress, which in this case would be this plane, the plane of SV. And directly the angle towards that other plane, or the fault plane in this case, is the dip. But that's not going to be always the case. But in this case, it happens to be the dip. And when you go to the Mohr circle, then you're going to have to do 2 times that angle. So it's going to be somewhere over here. And that's the point that we are interested in. All right. So sigma n is going to be the center plus the radius times cosine of 2 times 60 degrees, and tau is going to be the radius times sine of 260 degrees. Can you make that number, guys? Okay, 6.1 MPa, and let's say 4 MPa. That's something also very important that you keep in mind about significant digits. In this case, especially in geomechanics, we have a lot of uncertainty in measuring some of these values, SV, SH max, SH mean. So sometimes referring to with too many digits to a result, it doesn't improve anything. All right, so 6.1 and about 4.4 megapascals. That's the procedure. So, you know, it's relatively simple, but this case, I would say, is the simplest. And it can get a little bit more complicated, and we're going to see another example right now, but it's always the same procedure. I think, any questions? In this particular case, also, we chose the Mohr circle that was the biggest Mohr circle, but remember that we have 2 other Mohr circles here. And you could have done this for faults with strike east-west, and you could have also done with faults with a dip of 90 degrees. All right, so everyone understood this example? Let's see one a little bit more complicated, okay? Okay, here you have some nice drawings of what we have done in class. This is the problem that we just did. And now we have another problem over here. Okay. This is your data, fault and state of stress. And now you have a fault with a dip of 90 degrees and with a strike which is not east-west or north-south. It's at an angle. Okay? So in this particular case, what I'm going to suggest is that you make a top view draw of this problem. So let me put this on the side. I'm going to explain what I mean with a top view. And you have to be more or less precise with your drawing. Okay? If you're not a good drawer, then it's going to get a little bit complicated. But try to do this as all right. We know that the dip is 90 degrees, so I'm not interested in seeing what is the dip as in the other one, because I know it's 90 degrees. So I'm just going to draw it from the top, okay? And what this is telling me is that the strike is 60 degrees from the north towards the east. All right. So let me do this. Let's say this is the north and this is the east. 60 degrees is going to be somewhere over here. That's 60 degrees from the north towards the east. You can barely see. Let me make this a little bit thicker. That would be the line of the fault. But before I do that, I also would like to do the drawing of the stresses. SV is in the direction of the paper. SH max is 45 MPa, okay? And SH mean, it's oriented at 30 degrees from the north towards the east, okay? So that's going to be a line which is somewhere over here. 30 degrees from the north towards the east. So this one is 30, this one is 60, okay? All right. Probably I should have started with drawing the SH mean. And well, I missed the first step. First step we said, identify the stress regime, and in this case is what? Strike slip, very well. Strike slip. 2, we're making a top view drawing, and this is where it gets a little bit difficult. We need to draw these stresses. We need to draw a block on top of this, so this is going to be perpendicular to this, perpendicular to that, and perpendicular to these lines. So here I have SH mean in direction perpendicular to that. I have SH max and now I have these angles. Okay. This is just the data that I have. Inclination of SH mean, inclination of SH max. All right, so which circle, Mohr circle, should I use in order to tell what is the state of stress on this fault? Can you see that again in this case the vertical stress is not going to play any role in defining what is the shear stress and the normal stress, because it's in the same plane of the fault. So the fault is something like this, right? And whatever the value of vertical stress is not going to project on the fault, so it's not going to intervene at all. So the Mohr circle that I need, yes, Mr. Cosby.
Almost always have a dip of the strike azimuth of 90 degrees, or dip of 90 degrees.
For the ideal case, yes. In a strike slip, always for the ideal case, you're going to have a fault with a dip of 90 degrees. So, well, in this particular case, then, we're going to use, as you can see from here, we just care about SH max and SH min, and that's the Mohr circle that we need. And we'll figure the angles in a bit. Probably, you know, all the numbers, you can see them in my notes. So next step will be to compute sigma H max, sigma H min, and once you do that, you draw the Mohr circle for tau sigma n, and sigma H max in this case is going to be larger. So let's say this one is sigma H max, sigma H min. The tricky part of this problem is to get to know what is going to be the angle that I need in the Mohr circle. So let's say that we have the values of sigma H max and sigma H min, all right? We have the center of the circle, we have the radius. Now the question is, what is the angle that I need in order to go from the plane of sigma H max to the plane of the fault? What do you think that angle is?
60.
I need to go from this plane towards that plane. That's the angle. Or, which is the same, from this one towards that one. It is 30 degrees. And how I know that? Because if you use trigonometry, you will see that if this is 30, this is 60, this one must be 30, and if this one is 30 degrees, also, let me do, the easiest one is this one. This one is 30 degrees as well. Probably, I don't know if you guys remember these rules of the opposite angles with respect to two parallel lines. That's what you need to use in here. Yes?
Why are you going from the SH min, perpendicular to SH min from that parallel to SH min?
No, so I'm going always from the plane of the maximum stress, which is this one, to the plane of the fault. And that would be this angle, or, which is the same, this angle over here. That would be beta. So let me look for a more convincing explanation why that is 30 degrees. So I know this one is 30. Okay, I got it. If this is 30 and this is 60, this one should be 30, right? Let me zoom in. So if this is 30 and this is 60, this one must be 30. And because this is a right angle, this one must be 60. And because this one is a parallel line with respect to that one, this one must be 30. So it's all, rules of complementary angles. And therefore, what you need to look for here, it's a point somewhere over there, 2 times 30 degrees. And you know the center, you know the radius, you can solve that. And in fact, here you have the solution of the same problem and what are the values of those stresses. So for this part of faults, there are two things that I recommend or that are causes of why you should take a look more at the notes. First of all, some of these problems require a little bit more of thinking on your own and practicing to get them right. And I have several problems here that you can work with. And second, I was away last Friday, and I'll be away this Friday too, because the provost of research is calling me for a meeting of several professors, and I cannot make it to class. So I'm going to post some videos instead of coming on Friday to lecture. So I don't know if this is good news for you or bad news, but I'm going to miss you, but I'm going to send a video instead. But you know, all of these problems are there on the notes, and I put a lot of time on making some of these figures to explain them well and typing all these equations. So I hope that this is going to be useful for you to solve the problems and to solve the homework. All right, so you know, that's it for the 3D Mohr circle. That's everything what I want you to know. That we can use the 3D Mohr circle to calculate stresses, shear stress and normal stress on these lines. But whenever we need to calculate stresses for oblique planes, we can do that, but we're not going to do it in this class. I'm just going to tell you how it works, but we're not going to do it. Basically, you could do it also with the 3D Mohr circle, but it's a mess, like many angles, and then you need the compass, and we're not going to do that, okay? That used to be done a long time ago, but now we have computers, and we don't need to do that anymore. Instead of that, we use linear algebra. And basically, if you want to get stresses for oblique planes in these faults in here that are not aligned with any of the principal stresses, which, by the way, that would be the most common case in reality. The ones along the circles, that's not going to be very common. It's going to be actually quite unlikely. They could be close, but no, they're not going to be quite there. Most of them are going to be oblique faults. In order to solve that, what you have to do is to use the stress tensor and to change the coordinate system to project that stress tensor that we have right here on the plane of the fault. Each fault is going to have its own coordinate system, in this case made of these three vectors. The first element is going to be the dip. So that's a vector that goes down along the fault. The second one is the strike. That will be your middle finger that goes along the strike of the fault. And the third one is the normal vector to the fault. And now you can see that actually the strike that we use is not ambiguous anymore, because it's going to be the angle between the north and the direction of the vector of strike. So in this example, you have a fault dipping in direction southeast, and the angle between the north and the vector of strike is going to be less than 90. If you had the same fault dipping in the other direction, then your normal is not going to be in this direction, but it's going to be in this other direction. And the strike is not going to be, let's say, 45 degrees. It's going to be 180 plus 45. So now it's not ambiguous anymore. And it depends on in which direction the fault is dipping, what your strike is. So you can use these elements and their directions, the strike and the dip, and multiplying sines and cosines, and at the end of the day, you're going to be able to calculate two shears, the shear along the dip and the shear along the strike. The shear along the dip, is going to make a fault move up or down because it's along the dip. And the shear along the strike is going to make the blocks move in the direction of the strike. So let's say left and right. And depending which one you have, if you just have dip component, it's just going to go in direction along the dip. If you have strike component, it's going to go in direction along the strike. And that's why the stress regime, which is strike slip, is called strike slip, because the blocks move along the strike. And for reverse and normal, the blocks move in direction of the dip. When the hanging wall, which is the one which is on top, moves down, that's called normal. And when they go up, because they go normal, in the direction of gravity, that's referred as normal. When they go opposed to gravity, those are called reverse. And again, you can do all of these multiplications of matrix multiplication and then dot products and calculate this tau d, tau s. And at the end of the day, what you're going to be able to calculate all these points that are going to allow you to calculate what is normal stress and shear stress at any orientation. And let me remember the keywords I use for getting this image. I always forget. Let's try this one. I need to get my own example. I need to work on that. Okay, this one. All right, so, and what I mean with that is for all these faults, now we're going to be able to calculate, given their strike and dip, we can put them inside the Mohr circle and we can calculate what is normal stress and what is its shear stress. Again, we're not going to do that. If you want to do this, you're welcome to take my advanced geomechanics class, and we do lots of matrix multiplication in there. All right. Let me take advantage of the 2 minutes that we have in order to introduce the two last topics, or the applications of what we just learned. And these are going to be 3 applications. Let me go in another page. So why do we want to do this? Probably I'll just have time for one. First one, we want to know which fractures and faults are close to shear slip. And that's something which is called critically stressed fractures. These critically stressed fractures have a ratio of shear to effective normal stress which is similar or close to the friction angle. In terms of the Mohr circle, what this means is that if you have a given Mohr circle, 3D Mohr circle, and you have a given friction coefficient, which is not going to be just exactly one number, but it's going to be some heterogeneity, and there's going to be some values, a range of values, all of those faults and fractures which are in this section, those are the ones that are going to be called critically stressed. Because they are almost at the point of failure, or they might be failing at a given moment, but very slowly. And just one more thing, guys. When that happens, when you have critical stress fractures, and especially when you have brittle rocks, the permeability of the fracture is proportional to that ratio of shear to normal stress. So that's super important, because those fractures are going to be hydraulically conductive, and the others are not going to be hydraulically conductive. So this is going to give you permeability anisotropy as a function of the fracture direction. Okay, guys, if you want your exam, just stay here 5 more minutes. I'll give you those right now.